Well, my dear participants, we have already talked about simulation from exponential distribution. Now, today I am going to talk about simulation from weibull distribution. So, before that, I would like to show you the theory behind simulation from weibull distribution. Yes. Now I have to run the source code and then only see. We have to run this init. I don't know whether yes. So I will run the new code and we will make use of knit button, and we are running and we are making a document PDF document from the source code. See, now I am opening the document. From the exponential distribution. Inverse CDF method. A simulation from weibull. So before coming on simulation from weibull, actually, well, this is the simulation from weibull. Weibull distribution is defined as related to exponential distribution. Note that CDF of exponential distribution is fx is equal to 1 minus e raised power minus lambda x. Then CDF of weibull is nothing but C fx is equal to 1 minus e raised power minus lambda x raised power p. Here additional parameter p is being introduced, and it is this one, this p, this is the shape parameter, this decides the shape. So, to make use of the, where lambda stands for the rate parameter and p stands for the shape parameter of the distribution. However, in R, it is defined in terms of scale, not rate. Note that rate is equal to 1 by scale. Thus, CDF for weibull distribution is defined as fx is equal to 1 minus exp minus x by theta whole raised power p. Now what we have to do? We have to equate fx is equal to u, and that means 1 minus e raised power minus x by theta whole raised power p is equal to u, and that means if we transfer u to the left hand side and exponentiated part to the right hand side, it is 1 minus u is equal to e raised power minus x by theta whole raised power p. And this implies take logarithm of both the sides, log of 1 minus u is equal to minus x by theta whole raised power p. And this implies, see, if we transfer p to the left hand side, it will be minus log of 1 minus u whole raised power 1 by p, and you transfer theta to the left hand side. So this is the equation for the quantile. X is equal to theta into minus log of 1 minus u whole raised power p. Now following R code, so these are the R codes which we can run now. So we will go to the R codes now. Yes. So here we are defining scale is equal to 50. So we are fixing scale parameter 50 and shape parameter is 1.2 of weibull. Then we are simulating 5000 random values from uniform distribution. And then we can implement this formula. X is equal to scale into minus log 1 minus u whole raised power minus 1 by shape. So these are the simulated quantities. We can look into the simulated quantities, 5000 observations from weibull distribution with rate is equal to, with scale is equal to 50 and shape is equal to 1.2. Now we can make use of the curve d weibull, shape is equal to 1.2. So here first we will make the histogram. Histogram probability is equal to true, y lim is equal to this, and then on the histogram we will add a curve d weibull x shape 1.2, scale is equal to 2 and add is equal to true. And actually on this we can add a non-parametric density estimate. The function is density. And since we are adding on existing curve, on existing figure, it is not plot, it is lines, because lines is the low level graphic function. So when we run these codes, we are getting the curve. This solid line is because of the curve, exact curve, and this dashed line, it comes out because of the lines command, lines density, y density, compute density. So this is the non-parametric density curve estimated from the data, and we are getting these results. And this we have already defined for some other models too. Like here, if we talk in terms of simulation from, see here we are already doing simulation from exponential distribution using this. Then we add hist x prob, and then we can add a curve x rate is equal to 0.02, add is equal to true, LWD is 2. To add a non-parametric density estimate, lines command lines, density of x and LTY is equal to 2, color is equal to blue, and then we can add ebb line. So if we run the whole chunk, this kind of graphics. So, this is the non-parametric density curve and this is the exact curve of exponential and this is the histogram which is based on the simulated data. So, this way we can add. Similarly, suppose exercises on Poisson. Before that, I would like to talk about beta distribution, gamma distribution, exponential distribution. So, here also we have simulated RE, REXP. So, this is the simulation from 10,000 simulation from exponential distribution, and then if we want to make a histogram of this hist RE, prob is equal to true, and then we can add exact curve DEXP x rate is equal to 1, rate is equal to 1, add is equal to 2, LWD is equal to this thing, and we can add a non-parametric density curve lines, because here the high level graphic function is hist because it makes a histogram. Then we are adding a curve. So, add is equal to 2 makes this low level graphic function. That means it will add on existing plot. Then lines is also a low level graphic function. It will add the density curve estimated by non-parametric method into the same curve, and we will run and we will get the result. See. So, this is the exponential density, this is the histogram simulated on the basis of simulated data from exponential, a standard exponential. This is the histogram made on that very basis on simulated data. Then this is the exact curve of exponential with rate is equal to 1. But this one is the non-parametric density curve which adds on the existing plot, and this is because of this command lines, LTY is equal to T means dashed line. Similarly, for gamma distribution, suppose we are simulating gamma, 1000 observations from gamma distribution, shape is equal to 1.2, rate is equal to 0.02. So, we can simulate this data, and then of course, we can get mean which is nothing but 60, and then histogram on the basis of simulated data. Then we add a curve of d gamma exact curve with shape is equal to 1.2 and rate is equal to 0.02 and add is equal to true, and then we add a lines density y, LTY is equal to 2. So, here again lines density is the density estimate of y, and we are adding this as line LTY is equal to 2 means it is actually dashed line which is added on this. So, if we run this chunk, we are getting this. So, this is the exact density curve of gamma, and this is on the basis of non-parametric density estimation. More examples on gamma, but here we are not adding. Here also we are not adding. Beta distribution also we are not. Here R beta, 5000 observations are simulated from beta with shape 1 is equal to 3, shape 2 is equal to 3. Then histogram on the basis of probability, and then curve d beta x 3 add is equal to true, and then lines we are adding the density curve on this distribution. So, if we run the whole chunk, we will get this. This solid line is the exact beta distribution, histogram based on the simulated data. Then solid line is exact beta density with shape is equal to 3 and shape 1 is equal to 3, shape 2 is equal to 3. and this is the dashed line which is non-parametric density estimator of the density. Similarly, if shape is equal to 2 and shape 1 is equal to 2 and shape 2 is equal to 20, and we are again simulating distribution from beta distribution. So, this will be left skewed distribution. Haste probe and curve, we will add a curve on it and then we can add a line density. See, here it is right. Here since it is shape 2 is 20, so that's why it is right skewed. If shape 1 is 20 and this one is 2, it is left skewed. So, here I am talking of right skewed distribution, and this solid line comes because of the curve d beta x to 20. So, it is because of the curve, and this dashed line LTY2 is nothing but lines density. So, this is the non-parametric density estimator and we are getting both in the same curve. Now, inverse CDF method I have already talked, and then R commands. Here also, if we will simulate observations on the basis of inverse CDF method, lambda is equal to this, u is equal to uniform, lambda is equal to 0.02 and x is equal to minus 1 by lambda into log of 1 minus u. This is the simulated quantiles from exponential distribution with rate is equal to 0.02, then mean, then variance, then SD, then mean greater than 50, histogram on the simulated data, and we are adding a curve with rate is equal to 0.02, add is equal to 2, LWD is equal to 2. And then we can add a non-parametric density estimate curve. We are using the function lines, density x, LTY is equal to 2, color is equal to blue. Then ebb line, V is equal to 50, color is equal to red. So, if we run this command, it is like this. So, here this line is exact, this actually histogram is made on simulated data. This line is exact exponential curve with rate equal to 0.02, and this dashed line is nothing but it is a non-parametric density estimator of standard exponential. Note that simulated results obtained by using inverse CDF method are matching with the exact results both in terms of numeric as well as graphics. Then simulation from weibull distribution, fx is equal to 1 minus e raised power lambda x implies fx is equal to and then we define, here we are adding a shape parameter, so it becomes CDF of weibull, and then fx is equal to 1 minus CDF of weibull. We just equate CDF of weibull is equal to u, and then we solve it, equate, see fx is 1 minus e raised power minus x by theta whole raised power p is equal to u, and this implies you just transfer this u here, 1 minus u is equal to exp minus x by theta whole raised power p, and then take the logarithm of both the sides, log of 1 minus u is equal to, it will be minus x by theta whole raised power p, and then we can solve it for x. So, first we will transfer this to this side, so it will be minus 1 minus log of 1 minus log u, it will be whole raised power 1 by p, and then we will transfer this to this side, so this will be theta. So, x is equal to scale into minus log 1 minus u whole raised power p. So, here we are going to have a command to implement this. See, x is equal to scale scale we are specifying 50, shape we are specifying 1.2. Then we are simulating 5,000 observations from uniform distribution, uniform 0, 1, and then we are computing the simulated values, simulated quantiles from weibull distribution with shape is equal to 1.2 and scale is equal to 50. And then we make a histogram of this, and then we add a curve, exact curve of weibull with shape is equal to 1.2, scale is equal to 50, height is equal to 2, and then we add lines density, a non-parametric density curve on the figure. So this is the high level graphic function because it generates a new plot. Curve we are adding because add is equal to true is here. So it is a low level graphic function. It adds a curve here. Then lines density x. Then lines is also low level graphic function. So it adds a density and LTY is equal to 2. Line type is 2. So here the histogram is made on the basis of simulated data. Then we have plotted exact weibull distribution here, and then we add a non-parametric density estimator generated by the function density, and that is dashed line LTY is equal to 2. LTY is equal to 2. So they are in close agreement with the results which we are expecting. Now some exercises on simulation. Estimate the mean and variance of Poisson random variable whose mean is 7.25 and by simulating 10,000 observations from Poisson distribution, Poisson random numbers. Compare your results with the theoretical results. So we can do this problem by, we can solve this problem by x is equal to R-Poisson and R-Poisson, n is equal to 5,000, no, it is 10,000. 10,000 observations are being, and what is the value of lambda? Lambda is 7.25. So we are R-Poisson, there is a spelling mistake, R-Poisson. And then if we compute mean of x, it is 7.24, it is very close to 7.25. And then var of x is also 7.14. So it is very close to 7.25. And theoretically we know that expectation, that is mean of Poisson parameter lambda, expectation of a Poisson random variable is equal to mean, and variance also is equal to lambda. So this is a distribution in which mean and variance both are same and they are around 7.25. So through simulation we have established this result. Now exercise on simulation from normal 0, 1. See, simulate 1000 realizations of standard normal random variable z and use your simulated sample to estimate probability z greater than 0.25, so, and then probability of 0 less than 1.64, probability of 1.2 less than z less than 1.4, and probability of minus 1.2 less than z less than 1.3. So these problems we have to solve by using simulation. Compare your results with the exact result using P norm, z is equal to R norm, mean of z, and then to solve this z greater than 0 and z less than this one, 1.64. So first I would like to solve this problem. First we will define z is equal to R norm, it is 10,000. So actually what we need to compute probability of z greater than 2.5. So to compute this, we have to compute mean of z greater than 2.5. So its probability is 0.0057. 0.0057. So this result we have got on the basis of simulation. Now what should be the exact result? P norm and the value is 2.5, and since lower dot tail is equal to false because we want to compute probability greater than 2.5. It is 0.0062. So this is the exact result, 0.0062, and on the basis of simulation we are getting 0.0057. So they are in close agreement. So that means we can avoid P norm and we can make use of simulation. Another example, if we want to compute probability of z between 0 and 1.64. So this we would like to compute on the basis of mean and then 0, greater than z greater than 0, and z less than 1.645. So we can compute this mean, and this area is area under the normal curve between 0 to 1.64 is 0.4486. So this result we are getting, this probability we are getting on the basis of simulated data. Now see what exact result is. P norm 1.645 minus P norm 0. Again we are getting the same result, 0.4486 by simulation and 0.45 by using exact results. So here simulation result matches with the exact results. Similarly, in the case of see probability between 1.2, okay, now mean of z greater than 1.2 and z less than 1.45. So this probability is 0.0389 and we can verify these using p norm 1.45 minus p norm 1.2 and we are getting the same result 0.0389, 0.41, 0.04158. So they are matching. Similarly, we can compute this area under minus 1.2 to 1.3, minus 1.2 to 1.3. So here mean is z greater than minus 1.2 and z less than 1.3. So here area under the curve between minus 1.2 to 1.3 it is 0.79 and we can confirm this by p norm 1.3 minus p norm minus 1.2 and see 0.7902 it is we are getting simulation by simulation and by the exact result we are getting 0.788. So they are in very close agreement. Now in the next video I shall continue on these computation of these probabilities and simulations.